Rajeshwari MJ. She pursued her BE in Electrical and Electronics at the People's Education Society College of Engineering, Mandya. She pursued her MTech in VLSI Design and Embedded Systems at the Sri Jagadguru Balagangadharanta Institute of Technology, Bangalore. Her personal skills lie in good verbal and written communication skills. Her areas of interest lie in OOPS with C++, renewable energy sources, HVDC transmission, digital relays, automotive electronics, advances in VLSI design. She has also had papers presented at the national level, such as the Innovative Architecture for SoC Multi-Core Hybrid Processor, presented at the RNSIT, Bangalore.
Welcome to UGC lecture series of BSc Applied Electronics of semester 4. Today we are dealing with the subject Semiconductor Devices and Integrated Circuit. Let's start with the unit 4, lecture 3. The topics that we are going to discuss today are the MIM diode, that is metal insulator metal diode, the semiconductor light sources and the photo detectors, tunnel transistors. Let's start with the MIM diode. MIM means the name itself indicates the diode will have the structure metal, insulator and metal. And in the MIM there are many more MIM are there. If the MIM having the metal insulator and the insulator metal, which is having two insulator metal and on top of it metal 1 and below that metal 2. This is how the structure of a MIM diode looks. If the layer, the insulator layer is 1 and if the insulator layer is 2, if it is having 2 means it is also we called as a metal insulator metal diode. This is what the structure looks like, and these diodes are existed in the 1960s. Next, how this MIM diode works? This MIM diode works on the principle of quantum tunneling. What we studied in the tunneling diode, the same principle is applied in the MIM diode, but here the instead of P and N material we are using the both layer or both type of a material that are using here is metals. The two type of metal, that is M1 metal and M2 metal are used. There is a thin insulating material will be placed. This is how the tunneling effects will occur in a MIM diode. This is M1 metal and this is M2 metal. There is a thin insulating silicon dioxide layer. When there is a beam of electron which is entering towards the insulating materials, which is having an energy of E equals to EB, then some of the electrons that will go inside, that will penetrate the insulating material and cross the, that is what the tunneling effect, because some of the electron will absorb, some electrons will pass through this barrier and some of the electrons will reflect back, absorbing the electrons, absorbing the energy surrounding it. So, the electrons that reflect back from the barrier will have high energy than what it is before due to its reflection and also the absorption of energy from the surrounding. And the electron that which is passed through the barrier, which is traversed through the barrier, will have a property, and it is not like exactly like what the electron property that we found in this region, because it passed through the insulator where there is no conduction takes place, and the electrons that which reflect back from the barrier will have high speed electron movement. This is how current will flow due to the high movement of electrons, that is due to the reflection of electrons from the barrier, which is due to the absorption of energy from the surrounding. This is how the picture looks when it enters. Some of the electron which enters and some of the electrons will reflect back, that is stays in the M2, which is moving with a high speed. This is what the tunneling effect, and this is how the principle used in a MIM diode for a conduction of electrons. Next, we move on to its energy band diagram. Since already we said there will be two metal layers M1 and M2, this is the intrinsic thin intrinsic layer, and since we are using the two metal, the same devices, say metal 1 and metal 2, obviously the Fermi level will be on the same, both are using as metal, the Fermi level will lies on the same level, and we can expect the flux will be of same, that phi b 1 is equal to phi b 2. And also if we consider the current density across the field is also uniform, field will be also uniform, that is it is constant, because we are using both metal. Next we move on to another topic, that is semiconductor light sources. Semiconductor light sources are the sources where we are going to use the semiconductor as a light sources. And now we are going to discuss about laser, one of the semiconductor light sources. Laser means, the laser stands for light amplification by stimulated emission of radiation. Let us see how the laser principle is and how the laser works and what are the principle involved in it. Before starting the laser principle, we need to know the stimulated emission, absorption and spontaneous emission. Due to this, how we are going to emit the photon or light. The very first type is absorption. In absorption, this is energy level 1 and this is energy level 2. This is considered as lower energy level and this is considered as higher energy level throughout this session. Okay. When the photon is subjected to the electrons or atoms on the energy level 1, this is excited, the atom in the energy level 1 excited to E2. This is called absorption, because the photon is absorbed by the atoms on the energy level 1, that is lower energy, and it is going to the higher level 1 by absorbing the photon. Next, the h nu represent the energy of a photon, and in the spontaneous emission, the atoms in the energy level higher will comes down to the energy level, lower energy level, by emitting the photon of energy h nu. This is spontaneous emission. Now, the important thing, the stimulated emission on the principle which the laser works, when photon is applied for the atoms on the energy level, higher energy level, this will going to absorb this h nu and it will come back to the lower energy level, releasing the same energy, h nu energy of photon, and this is also going to be have another photon, that is h nu, that is already there. So, in stimulated emission, what is going to happen? The V2 will not going to absorb any sort of photon, simply it is excited or decayed from E2 to E1, emitting the photon of energy h nu, and which will be amplified because of another photon already existed. So, these two are combined, result in the amplification. This is how the stimulated emission takes place. So, we know the stimulated emission. Now, another important requirement for laser action is inversion, how this inversion takes place, and also another thing, the pumping will happen. So, we know that in a laser, the non-equilibrium distribution of atom among the various energy level will be there due to the material that we are using having a non-equilibrium distribution of atoms. So, for very first thing that we need to know is the inversion. In the inversion process, the population of atom in the higher energy level will be more compared to the lower energy level. Usually in general, what it will be there in general statement, for a laser action in a higher energy level, the population of atom should be more than the population in the atoms in the lower level. This can be achieved by a inversion process, that is by exciting the atoms from the lower level to the higher level, making the population of atom in the higher level more. This process is called as inversion. That is what we observed from the figure. N2 is greater than N1, where an inversion process is achieved, where the atoms in the N2 will be more than N1. Next, the pumping action. For exciting the atoms from the lower level to higher level, we need a large energy, so that the atoms from lower level will move to the upper level. So, this can be achieved by a pumping action. So, in a pumping action, we need 3 layers, at least 3 minimum layers will be required for the pumping action, that is we consider as E1, E2 and E3. So, now we come to know that population, inversion and pumping action, that stimulated emission. Based on these 3 principles, we can have the laser effect. So, next we move on to principles of laser. Now, it is come to easy, we know that how the population inversion and pumping effect and also the stimulated emission is takes place. So, first we consider the atoms in the energy level 1 will be there. This will be excited from the E1 to E3. What do you mean by this? This E1, the atoms excited from E1 to E3 means it is a pumping action, because from E1 to E3 it requires large energy for the excitation of atom. This is achieved. So, when all the atoms is pumped from E1 to E3, there is enough atoms in the E3. There is a large number of atoms in the E3 compared to E2. So, this is called as a inversion process, and once it is reached, when we give the photon, this will be absorbed by the atoms in the E1, it will going to excite in the E3. There is another energy level, that is metastable state in E2. So, when all the atoms are on the energy level E3, it will going to decay from E3 to E2, releasing the photons of h nu energy. So, we get a photon of h nu energy, and if we consider E2 as a long lived state, atoms from E2 will decay E1 rapidly. It will stay here for long time, and once the population increased here also, again it start decaying from here, from E2 to E1, releasing again the photon. This will results in a coherent photon. That is how we will tell in the next slide. When one atom in a E2 decays spontaneously, when enough population is there in a E2 band, any one of the atom decays means the photon will release. This photon will hit the neighboring atom, spontaneously releasing the photons back to back. This makes this will result in a coherent photon. This is how the coherent photon will produced. Next we move on to laser diode principle, that what we are studied till now. Make some points. Consider p-n junction. In p-n junction we are speaking about the diode. So, we are considering p-n junction. In order to design a laser diode, the p-n junction must be heavily doped. So, the laser action will be now takes place by p-n junction diode. And if we want to have the laser action, we need to heavily dope p-n junction. So, in other words, p and n material must be degenerately doped. So, if we are going to degenerately dope means both we can achieve the non-equilibrium condition. By degenerating, Fermi level of n side lies in the conduction band and the Fermi level of p side will lies in the valence band. This is the important things. After doping we can see in energy band diagram. This is what the difference when compared to the other diode than to the laser diode. Next, how the energy band diagram of a laser diode looks after the heavily doping. It is like this, as I said, and in the n type the conduction band merges with the Fermi band. This is what we are observing, and here in a p type the valence band merges with the Fermi level. This is what we can observe from the p type. There will be minimum gap. So, with the potential or voltage equal to potential barrier voltage, we can make the electrons to flow from n to p. In the forward bias, if electron, that is the band energy EV, that is band energy voltage is greater than the energy band, the potential barrier voltage is greater than the energy band voltage or energy band gap energy, then the conduction will takes place due to the potential barrier will going to reduce and it is almost in a 0. This is how when EV is greater than EG, the inversion takes place, the conduction of electrons will takes place. Due to the inversion, the photons will be released, and due to this we can achieve the electrons flow in a diode. Let us have a short break. Welcome back after a short break. Application of forward bias. Suppose that the generated dope p-n junction is forward biased by voltage greater than band gap, that is EV is greater than EG. that is what we can achieve the forward bias. When EV is greater than EG only we can achieve that forward bias, so that we can deplete the depletion region, the conduction takes place. The separation at the forward bias, what happens, the separation between EFN, that is N type Fermi level, and the P type Fermi level is now the applied potential voltage, that is EFN is equal to EFP, that is equal to the applied voltage. The applied voltage diminished the built-in potential barrier, that is EV, not to almost 0. So, the conduction takes place. So, the conduction can now flow to the P type, the electrons can now flow to the P side and holes now flow to the N side. Next, population inversion. How the population inversion will be takes place in the diode when it is forward biased. There is no the population inversion between energies EC and near EV are around the junction. This is how the population inversion takes place. In the conduction band, more electron will be there than the valence band. This is a lower energy, this is a higher energy, where in the conduction band more electrons will be populated here, and the electron volt, that is the potential voltage, potential barrier voltage will be EB, energy band gap will be EG. This is a N type Fermi level which is merged with the conduction band, and this is a Fermi level of a P type which is merged with the valence band. And here the current pumping from lower band to higher band already it is happened in the due to the forward current, the pumping action will already placed, due to this the inversion happened. So, the more number of electrons will be present in the conduction band, due to this we can achieve the population inversion by applying forward current to the diode. The laser action having some of the important points to be noted. The population inversion region is a layer along which the junction, along which the population inversion takes place. That layer is called as an inversion layer or active region. Where the population inversion is there, that region we can call it as an inversion layer or an active region. And also now consider the E is equal to Eg. When this action will be exist means when the energy of the photon will be equal to Eg. And obviously photon can exist from excite electrons from EV, since there is no electrons. When this is when E is equal to Eg happens, there will be no electrons present in the valence band, because already due to the population inversion all the electrons will be in a conduction band, there is no electron in the valence band. However, the photon can stimulate electrons to fall down. When we stimulate the photon, when we are going to give the photon will comes from the conduction band to valence band. Since this happens, again the photon will release due to the movement of atoms from the higher to lower level. This increases the gain, and this region is called as an active region, where the population will be more, the inversion region where the population of atoms are more, and the gain of optical gain also increased here. For successful lasing effect, these are the things we need to be remember, that optical gain achieved by population inversion method, we can achieve the optical gain. As I said, the population inversion method will be through this we can get the optical gain. Then optical feedback is very important. So, once we get enough photons due to the excitation of atoms from higher level to lower level, this photon is again used by a feedback. What are the feedbacks that we can give is, this can be achieved by device configuration needed to increase the total optical amplification by making photons pass through the gain region multiple times. As I said, the gain region is formed by the population inversion. In this region, we need to make the photon to move to and fro, so that we can achieve the stimulated emission again and again. Insert 2 mirrors at each end. This is another thing we can achieve the optical feedback. This insert 2 mirrors at each end, this is another method of getting optical feedback. This is the active region, that is what we observe where the population inversion takes place. Here the enough photons are released, and between this this is a feedback, optical feedback, where it is reflected 2 and 4, and it is partly reflected and it is partly transparent, and here some of the photons are going out, which is a laser, which is due to the laser action, which it is going out due to the partly transparent of a feedback. And now in the figure it is going to observe the intensity, how the intensity vary with the wavelength. As the wavelength increases at some resonant point, it reaches peak value like r is equal to 0.4 or r is equal to 0.7 and r is equal to 0.9. The resonant will reach the peak level and the intensity will be more. Next, another topics, the photodetector. What do you mean by photodetector? Means semiconductor device which will convert the optical signal into electrical signal, that is called as photodetectors. Hence we called it as a photodetectors. There are several types of photodetectors, that is photodiodes, phototransistor, photon multipliers, photoresistors are there. Now we are going to discuss about photodiodes. Photodiodes meet most requirements, that is why it is going to use widely. In the photodiode we are going to know about one of the type of photodiode is pin diode, that is positive intrinsic negative diode. We are going to use two type of material and intrinsic material also, that is p type material, n type material and intrinsic or pure silicon is used in a pin type diode. And also the pin type diode is always used as a reverse biased for a normal operation. Since in the reverse bias there is no current flow, the intrinsic region is fully depleted of carriers, no current will flow without illumination. So, this type of diode is always used for normal operation in reverse bias mode. Next, how we are going to make p type and n type photodetector? Let us see, n type diode is formed by doping acceptor and p type diode is formed by doping donor. This is how the n type and p type diode looks. Next, what is pin diode? Pin diode is consisting of p type and intrinsic, that is pure semiconductor and n type material are formed, placed together is called as pin diode. Here hole and electron are concentrated. In intrinsic semiconductor, hole or electron are uniformly concentrated and it is pure semiconductor. Next, the pin diode will have enough depletion layer, enough intrinsic material. So, this intrinsic material will act as a depletion layer. The p type will be having a electron diffusion and the n type will have a hole. This will going to due to the diffusion process, the electrons in the p type will move to the depletion layer, that is the intrinsic layer, and the holes in the n type region will move to the intrinsic layer. So, this will going to increase the carrier drift current in the reverse bias, and the energy band diagram of a pin diode looks like this. The p and n will going to produce current will when the photon are illuminated to the depletion layer or intrinsic layer. The photon which is having energy greater than Eg, which is sufficient. So, the depletion layer will have enough carriers. It is intrinsic which is pure, but even though there are some electrons or holes will present inside, that will be illuminated by photon, stimulating photon having energy greater than Eg. So, the photo generated hole will move to the p side and the photo generated electron will move to the n side. Next, we know that there is no need of bias voltage in a diode detector, since it is going to work in a reverse bias mode. Typically the width of depletion layer region is less than several micrometer, because the depletion layer is very thin, no need of any bias voltage. This diode will going to act as a detector because of eliminating the photons on the intrinsic layer. The high electric field across the p-n junction makes charge collection possible for the diode without external bias because of very thin depletion region, and also the built-in potentially also is less because of the thin depletion layer. It is of 1 volt. The electric field across the p-n junction is very high, so that is greater than 10 to the power of 3 volt per centimeter. As I said, this photodetector is worked on only in a reverse bias mode. How it works when it is connected for a reverse voltage, when a reverse voltage is applied. When reverse voltage is applied, the depletion layer is already increased due to the intrinsic layer, we are going to give a very less voltage. When we give the photons on the p type material, the holes in the photons will excited, free holes here will going to move to the intrinsic layer. This makes the intrinsic layer electric field more. This is how where the region the electric field is more in the intrinsic layer. The intrinsic region can be n type and that is lightly doped, and to make a low resistant contact, a highly doped n type, that is n plus layer is added here for making it low resistance, so that the current will flow easily from intrinsic layer to n plus layer and across the resistor. What is the physical principle of photodiode? As a photon flux phi penetrates, this photon flux phi having h nu energy which will going to penetrate into the semiconductor, it will absorbs, this will going to absorb some of the energy and the whole will going to move to the intrinsic energy. This and the power, if alpha s of lambda is the photon absorption coefficient at a wavelength lambda, the power level at a distance x into the material is what? What is the power level when the photon absorption coefficient is alpha s of lambda and at a wavelength of lambda? What is the power level at a distance of x, which is given by p of x is equal to p in e to the power of minus alpha s into x, that is a distance. Once the photon absorbs energy, the photon will give the holes in the p type will absorb the energy from the photon. This will move to the intrinsic material. This will going to attract the electrons in the intrinsic material, which going to create the high electric field. Thus current will going to flow. This current is represented as IP, that is a photo current, and which is going to flow through the resistor load resistance RL. Next we move on to physical principle. As we know, the physical principles of a pin diode will works on the reverse bias and radiation greater than band gap energy. We need to give a radiation that should be greater than band gap energy. Due to this excite a valence band electron into the conduction band. The excitation of electron from the valence band to the conduction band takes place due to the radiation that we are going to give having the energy greater than the band gap energy. Due to this causing a current to flow in an external circuit. So, the cutoff wavelength can be find out in the pin energy diagram when lambda c is equal to hc divided by Eg, that is equal to 1.24 divided by Eg electron volt of micrometer. Cutoff wavelength is depend on purely the Eg, that band gap energy Eg. This shows the cutoff wavelength lambda c is dependent on Eg. As Eg increases, the lambda c will decreases. Next, the quantum efficiency eta is the number of electron hole carrier pairs generated per incident absorbed photon of energy h nu, and is given by the efficiency. The quantum efficiency is given by number of electron hole pair generators divided by number of incident absorbed photons, that is equal to IP divided by Q whole divided by P in divided by h nu, where IP is called as photocurrent, that is generated by a steady state optical power P in incident on the photo detector. Next, the last topic, the tunnel transistor. This tunnel transistor we are considering the FET tunnel transistor. In a FET tunnel transistor, it is looks like a same FET, but here the FET will works on a principle of tunneling principle. So, the structure of tunnel transistor is somewhat slightly different than the common FET, where the P and N material in between the intrinsic material will be there. Since in the FET we are going to vary the depletion layer width by the gate current, but here the electrostatic potential of intrinsic region is controlled by gate terminal. This is the difference between the FET, the common FET and the tunnel, and here the quantum tunneling effect is used for a electron motion, but in the FET we are using thermionic emission. Next, the device operation. Due to the tunneling effect, as I said, the valence band, the electrons are accumulated in the valence band, which will going to touch the conduction band of a intrinsic region. If it is having in a p region, when more number of electrons are accumulated, this more number of electron going to move to the conduction band of intrinsic region when the valence band is merged with the conduction band of a intrinsic region, so that the conduction takes place, the current flow in the circuit due to the tunneling effect. And due to this we can achieve current flow, that is drain current will be get even for the lesser voltage. For a common FE, common MOSFET or FET, we will get a drain current for 60 volt per decade, but for a TFET we get less than that, less than 60 millivolt per decade we will get. This is the advantage of TFET than a common FET or MOSFET. The summary that till now in the session, that what we studied about M diode, that is a metal insulator metal diode. This metal insulator metal diode works with the principle of quantum tunneling. And next the laser diode, that is one of the semiconductor light source laser diode, where we are going to use a PN junction diode for laser action. And in a pin diode, that is one of the photo detector, which is going to convert the optical signal into electrical signal. We are going to study the pin diode characteristics, and the pin diode works only in the reverse bias condition, and it is going to electrons conduction will takes place by the absorption of photon. Due to this, the electron, the conduction band will going to move to the valence band. Due to this, more number of electron will present in the conduction band. Due to this, the conduction of current takes place. And finally, we study the tunnel transistor. Tunnel transistor works on the principle of tunneling effect. Due to tunneling effect, we can get the drain current with the less gate voltage, and we are going to control the electrostatic potential with the help of gate voltage, whereas in a common FET we are going to control the drain current by applying the gate voltage, but here we are going to control the electrostatic property of the intrinsic material with the applied gate voltage. Some of the questions of this session are: what is laser diode? Describe the principle of a laser diode. What is a pumping mechanism in a laser diode? And explain in terms of the PN junction what is pin diode, what is tunnel diode. For further reference, you can go through the website, or you can refer the textbook Electronic Devices and Circuits by G.K. Mittal. This ends up the session. Thank you.